All right, so today I'm going to introduce you to the idea of what's called first derivative analytics. It's analyzing maxes and mins, relative and absolute stationary points, all using the first derivative test or first derivative analytics. So I'm going to introduce you to that idea. Okay. We're going to play with this a minute. This is very informal. What I'm going to do right now is just going to give you an idea. So I want you to set up sort of a table. The top row is going to be something called intervals, and the bottom row is going to be the derivative. The intervals we're going to look at are x less than a, and then the interval from a to b, and the interval from b to c, and then x greater than c. So we're going to do this in a hypothetical situation, okay, using the letters A, B, and C. So A, B, and C stand for critical points. They are the critical points we've already found. Maybe we've already done the work, and we've cross-multiplied, and we've set our derivatives, and we've found our horizontal tangents. That's what A, B, and C are. A, B, and C are my critical points. So around my critical points, I'm going to set up intervals. And what you might come up with is something, you might be given something like this. And I'm going to help you learn how to read that and what that means in terms of analysis. Plus, minus, minus, plus. Okay, on a chart like that, what that means is on the interval where x is less than a, x is less than that critical point, the first derivative is always positive. If the first derivative is always positive, we know that derivative is the same thing as what? Slope. If the slope is always positive, what is the graph always doing? The graph is always going in what direction? Graph is going up. All right, so what we have to understand is that, actually we'll add another line beneath here, is for just regular f of x. And f of x is increasing. It is going up. Then we pass the critical point of A, and we move into the interval between A and B. So B is the next critical point. So what happens between those two critical points? Well, according to the analytic chart I've given you, f prime is negative. What that means, if f prime is negative, then the slope is negative, which means the function is decreasing. So this graph just changed direction. It was increasing until it got to the critical point of A, and now it's decreasing between the critical points of A and B. So what can you tell me about A? Using vocabulary. It's not stationary. What is it? If I just changed from a function that was increasing, I got to A, and all of a sudden, now I have to start decreasing back down. What can you tell me about A? A is some kind of max. Okay, I don't know yet if it's an absolute or a relative, but it is a max. So right here, A is max, some kind of max. All right, I've gotten to critical point B, and now I'm going to pass critical point B and move on towards critical point C. But according to the analytics, what is the slope continuing to do? The slope is continuing to decrease. And so the slope is negative, so the function is continuing to decrease. And so if I have a critical point, but the graph doesn't change direction at all, that is called a stationary point. So now you can tell me B is a stationary point. I'm just going to abbreviate that as stat. Now we arrive at critical point C. And critical point C, after that, after I pass critical point C and move on to the next interval, I now have a plus in my analytics, which means that my derivative is positive, My slope is positive, and so my graph, my f of x, is switching back to increasing again. So what can you tell me about critical point C? It is a min. Can you draw that picture now for me? All right, so let's slide this up here a little bit. We know that A is a max, C is a min, B is a stationary point. Something that might work for that, A, B, and C. We know that, according to the analytics, before it gets to A, the function must be increasing. So my function must be coming up. And once it passes A, it changes to decreasing. As it goes between A and B, it must be decreasing, but B is a critical point, which means it has to have a horizontal tangent. So as I approach B, I need to approach a horizontal tangent. So I'm not just going to go to B like that. That's not a horizontal tangent. As I approach B, I'm going to approach it more like, that's a little much. I'm going to approach it more like that, so that I'm approaching a horizontal tangent. As I leave B and move towards A, I'm leaving a horizontal tangent at B, and I'm coming towards C, but I'm still decreasing. And I need to approach another horizontal tangent, this time at C, so I'm going to approach it as a horizontal tangent. And at C, I finally change direction. And I'm going to turn and now change from this decreasing. I reached my minimum, and I am going to change to increasing, which now I don't have any other critical points. And because there are no endpoints, we can now tell that although A is a max, it's relative. It's a relative max because my endpoint that was heading off towards C, the section of my graph that's heading off towards C, doesn't have an endpoint. It just keeps increasing and increasing and increasing and increasing. And so this is a max, but it's a relative max. Yeah?
How do you know there's a horizontal?
Oh, I would have told you that already. Like when we had done our math earlier, we would have identified them. We kind of jumped in where we'd already done that. Okay, and so this one is a relative max. This one is a relative min. Now we'd need to find the y values, and we could do that if we had the actual function. We'd have to actually plug our numbers in to find the y values. And we still know that S is B is a stationary point. That's the idea of first derivative analytics. So what we're going to do is I'm actually just going to build on number 37, since Megan asked us about that. We're at a great point with number 37, and we're going to see what we can figure out with some first derivative analytics. So we're going to just jump in. I'm going to ditch the example that I was planning to show you, and I'm just going to use hers because it was a really good one. So let's review what we had from 37 already. I'm just going to copy a couple things that we've done already. We know that in 37, the question itself was it was x times the square root of 4 minus x squared. The domain on that is -2 up to +2. We found the first derivative to be 4 minus 2x squared over the square root of 4 minus x squared. And we'd already done the calculus, and we found that we've got horizontal tangents at critical points. Our critical points were rad 2, negative rad 2, and our endpoints were 2 and positive rad 2. And these two were the horizontal tangents, and these two were vertical. So now we're going to do first derivative analytics on this to help me determine where the function is increasing and decreasing, where the maxes and mins are. So we're going to take this same number 37 and we're going to create intervals. Now this one has endpoints. So I need to create my intervals in numerical order, going from smallest to biggest, around all of our our endpoint. So here we go. I'm just gonna, that's about all we need. Our intervals start with a closed interval. They start at -2 because that's the end point. What's the next, if I'm arranging these in order, what's the next critical point I come to? -rad2. I do not include -rad2 in the interval that is open. Then I'll go from -rad2 up to the next interval, or the next critical point, which is +rad2. Then I'm going to go from +rad2 up to my last critical point, which was the end point of just regular 2. So those are my intervals that are going on here. Start at 2 endpoints, and I have the critical points in between. And so then we want to look at what f prime is doing so that we know what f of x is doing. Okay, I need you to pick me a number that's in the interval between -2 and -rad2. 0 is not in that interval. 0 would be great. 0 would be great for this one. So keep 0 in mind. Okay, for sure we'll do 0 here. But I need a number that is within the that interval. All right, well, what's the approximation for rad2? Do you guys know that? Okay. 1.414-ish. All right, so give me a number that's between -2 and -1.414. Give me a fairly nice number. -1.5. Sure, -1.5 is great. All right, what I need you to do with -1.5 is plug it into the derivative. I don't need an exact answer. I just need to know, is it going to be positive or is it going to be negative? So take -1.5, plug it into the derivative, and I just need to know if it's going to be a positive or a negative number. I don't even need to know exactly what it is. Does anybody have that? Well, double check. I have a vote for a positive and I vote for negative. Okay, so one of you is right. That's fine. Get your calculators out. Okay, we're estimating here. Plug in -1.5, square it, multiply it by -2, put it in the denominator, and just tell me if you get a positive or a negative number. Not to the regular function, into the derivative function. We're doing a first derivative analytics here. Does anybody have it? Because I haven't prepped this problem because this is not the problem I plan to do today, but this is going to work great. It is a negative number. What does that mean that the function is doing? If the derivative is a negative number, what is the function doing? It is decreasing. All right, now, Cassidy, pick me a number between -rad2 and +rad2. 0. Okay, let's plug 0. This will be a lot easier. Plug 0 into the derivative function. Now, you don't even need a calculator to do that, to plug 0 in. Are you going to get a positive number or a negative number? Okay, we are going to get a positive number, which means that my original function is increasing in that interval. And then finally, we'll pick another number that's in the last set of intervals, so probably just for symmetry's sake, we'll pick +1.5. Okay, if we plug +1.5 into the derivative and square it, we should get the exact same thing as we did when we used -1.5. So that will be negative again. So this is back to decreasing. So my function was decreasing for a little while, increasing for a little while, and then decreasing again. Yes?
Because it includes 2 and -2, could you plug those in?
No, because those, if I plug into a -2, I'm going to get 0 in the denominator,
Oh, right.
which is why I have a vertical tangent there. Okay, so could we sketch what's going on here? All right, those critical points did have y values that we had found earlier when we were doing our homework, or that lesson. So we found out that the point was -2, 0. We also had the point +2, 0. We had -2, negative rad 2, negative 2, which is about down here. Negative rad 2, negative 2. And we had positive rad 2, positive 2. And our analytics tell us that at the end point of negative 2, 0, we should be leaving a vertical tangent. So we should be coming fairly straight down as a vertical tangent. But from there, I'm going to be decreasing until I get to this point here. And when I change from decreasing to increasing, I've now achieved a minimum. And now I hit my horizontal tangent. And now I'm going to increase all the way until I get to, and I hit another horizontal tangent. And then I come decreasing again and hit a vertical tangent back at my end point. That looks an awful lot like part of a sine graph. Now it's not, because we know the original function wasn't a sine graph, but it kind of has that general shape. And you can clearly identify what each of these points are here. All right, so negative 2, 0, that first end point, it's a max because it's higher than a whole bunch of stuff in its section, but is it the absolute max? No, it's relative, or another word they say is local. Local and relative mean the same thing, so we could call it a local or a relative max. Then we get to negative rad 2, negative 2. That is an absolute min because it's the smallest. That's the lowest y value. Then we get to positive rad 2, 2, which is our absolute max. And then what about the last endpoint? What kind of number is it? It's a min, but it's only a local or a relative min. Yeah. Say that again? Yes, and we're going to talk about that the day we do second derivative analytics. Okay, this is first derivative analytics, so it's coming. All right, let's try another one. All right, so analyze the behavior. We'll do this one from start to finish. We're not going to, cheat and take like number 37 like we did. Analyze the behavior of the following function. All right, our f of x is going to be x to the 5th minus 5x to the 4th plus 5x cubed plus 20. So analyzing the behavior means find all the critical points, end points if there are any, extreme values, and find the increasing and the decreasing by doing first derivative analytics. So we need to start, this has no endpoints because the domain is all real numbers, and so we have no endpoints on this particular function. So we need to move on to finding the critical points. So we'll find f prime. So 5x to the 4th minus 20x to the 3rd plus 15x squared. We'll need to factor that. So I'm going to pull out a 5x squared because I noticed that it has it in common, and I'm left with x squared minus 4x plus 3. That factor's great too. So I'm left with x minus 3 and x minus 1. So I will take that first derivative, and I'll look for horizontal tangents by setting it equal to 0, and I'll look for vertical tangents by setting it equal to 1 over 0. So 5x squared times x minus 3x minus 1 setting equal to 0, and 5x squared times x minus 3 times x minus 1 set equal to 1 over 0. Now, 1 over 0 is not going to produce any vertical tangents. There are no vertical tangents. You kind of should already know that because this is a kintic function. It's a degree 5. It's a polynomial. Polynomials don't have vertical tangents, but they have lots of horizontal tangents. So my horizontal tangents are going to be at the critical points 0, 3, and 1. And those are all going to be horizontal tangents. But which one's the max and which one's the min, maybe which one is the stationary point, I need to do a little bit of analysis on that. So I'm ready now to do my first derivative analytics. So I'm going to set up my intervals. Since I don't have an endpoint, I'm just going to do x less than 0. My next interval will be between the critical points of 0 and 1. And my next one will be between the critical points of 1 and 3, and then x greater than 3. So those are my 4 different intervals. And I'm going to look at what the first derivative is doing so that I can make a conclusion about what the original function is doing. Remember, when you're doing these analytics, when you pick a number in the interval, it has to get plugged into the derivative, not into the original function. If you plug it into the original function, you'll get the y value. I want to plug it into the derivative function, so I'm figuring out what the slope value is doing. That's what I'm more concerned about. All right, so we pick a number less than 0. Give me your favorite number less than 0. -1, okay? I always recommend plugging it into the factored form of the derivative because I find that the math tends to be a lot easier if I'm plugging it into that. So I plug in -1 into 5x squared. That'll be positive. I plug -1 into x minus 3. What will that be? That'll be negative. If I plug -1 into x minus 1, what will that be? So I've got a positive in the front times 2 negative factors. So overall, I'm going to have a positive derivative, which means my original function had the behavior of increasing. All right, pick your favorite number between 0 and 1. 1/2. Okay, plug it into the 3 different factors. If I plug 1/2 into 5x squared, that'll be positive. If I plug 1/2 into x minus 3, that will be negative. If I plug 1/2 into x minus 1, that will also be negative. So I'm looking at positive, negative, negative, which is positive again. So what have I automatically found is happening at the number 0? If my function increases, but appears to approach a horizontal tangent, and then continues to increase again. That is a stationary point. So we've now identified a stationary point at 0. So 0 is stationary. Then we pick our favorite number between 1 and 3, maybe the number 2, and we'll check what's happening to the function. So of course we know 5x squared will be a positive number. If I plug 2 into x minus 3, that will be negative, and if I plug 2 into x minus 1, that will be positive. That's 2 positives, 1 negative, so overall that's a negative. So I have my first change. My function is now showing a change in its direction, a change in its behavior. And so if my function is changing from increasing behavior to decreasing behavior, what can I confirm is happening at the number 1? Okay, 1 is a max. And then finally pick our favorite number that's greater than 3. We'll just pick 4. If we plug 4 into each one of the factors, we're guaranteed to have a positive number. And so my function changes to increasing again. And so now I've changed direction another time. And so now I know that what's happening at 3 is that 3 is a min. So I have the function, I've identified what the extreme values are, I've identified the intervals of behavior, and I could sketch a graph of this, or I should be able to, if I knew all the y values. So I could plug 0, 1, and 3 back into the original function and get their y values. Now, I'm not going to do that right now, but I'm just going to show you what this would look like. If something is increasing and then approaches a horizontal tangent and continues to increase, its graph is going to look like this. I am increasing but approaching a horizontal tangent, and then I'm going to leave the horizontal tangent and continue to increase. That's what that graph is going to look like. Then I have to approach another horizontal tangent, and I'm going to change direction. That wasn't very nice. And then I'm going to approach my last horizontal tangent, and I'm going to change direction one more time. Does this function have any absolute extrema? No, because the endpoints, because the domain is all real numbers, the ends of these graphs are approaching negative and positive infinity. So it has no absolute extrema. It does have one stationary point. It has one local max, and it has one local min. All right, so Ricky, Caitlin, Megan, I'm wondering how you feel about the questions you were asking earlier. How can you tell if it's a min, a max, or a stationary point? It's all about the change in direction. If the behavior, the analytics show a change, then you've got some kind of max or min. So this is going to lead you to writing sentences to justify your answer. Okay, we're not going to do that quite yet today, but you'll need to back it up. You'll need to be able to say, 0 is a stationary point because the first derivative indicated a horizontal tangent, but the slope didn't change. It was from increasing to increasing, and because there was no change, it's stationary. 1 is a max because there's a horizontal tangent there, and the slope changed from positive to negative, increasing to decreasing. So there's always going to be a because statement, and we're going to practice that later in the week. All right, so that's first derivative analytics. There are 11 problems tonight for you to perform this. Some of them have square roots, like 37. Some of them are polynomials, like this one we just did. You're going to want to find the derivative, find your critical points, and then test the intervals of your critical points to find out the behavior.